May 23, 1854. Crystal Palace Exhibition Hall, Manhattan. The crowd of building developers and European-trained engineers gathered that afternoon would witness something that challenged everything they believed about vertical construction safety. Above them, a Vermont mechanic named Elisha Otis stood on a wooden platform, suspended 18 feet in the air by nothing more than hemp rope. In New York's financial district, no building rose above 5 stories. Not because of engineering limits, but human ones. Deadly rope failures killed workers every month when industrial hoists snapped without warning. European engineering wisdom declared it impossible to build safely beyond 75 feet. American developers refused to risk their investments on unproven mechanical contraptions. The established truth seemed unshakable. Hemp rope breaks, people die, buildings stay low. But Otis had designed something different, a spring-loaded safety mechanism that European experts dismissed as unreliable American novelty work. As hundreds of skeptical eyes watched from below, Otis raised his hand and gave the signal. His assistant lifted the axe. The rope that held him suspended above the crowd was about to be cut. What happened next would either prove the doubters right or change Manhattan's skyline forever. The morning fog still clung to Manhattan's cobblestone streets in September 1852 when the construction foreman at the New Merchants Exchange building made his daily calculation. 5 stories, 78 feet from sidewalk to roofline. Beyond that height, he knew from bitter experience, the mathematics of human nature defeated the ambitions of architects. The upper floors of any building taller than 5 stories rented for half the price of ground-level space, not because of structural limitations, but because New York's business class refused to climb more than 75 stairs twice daily. The established wisdom ran deeper than mere convenience. European-trained engineers who had emigrated to New York's booming construction industry carried with them decades of calculated certainty about the vertical limits of commercial architecture. Johann Rapp, the Prussian-educated structural engineer overseeing the Exchange project, had studied under masters in Berlin who could recite the weight-bearing capacity of every known building material. Their conclusions were mathematically precise. Beyond 5 stories, the economic equation collapsed. Rental income per square foot dropped by 50% while construction costs per floor increased by 30% due to the additional structural support required for height. The deadly reality behind these calculations lived in the industrial hoists that already served New York's warehouses and factories. Every construction site, every furniture manufacturer, every textile mill relied on rope and pulley systems to move heavy cargo between floors. Hemp rope, twisted, from manila fiber and rated for specific weight loads, connected wooden platforms to steam-powered winches or manual capstans operated by teams of workers. The system functioned adequately for freight, but carried an accepted mortality rate that no responsible building owner would impose on paying tenants. 2 weeks earlier, the morning newspapers had reported another routine industrial death at the Haughwout Brothers Furniture Factory in Yonkers. The freight hoist's 3-inch hemp cable had parted without warning while carrying a load of mahogany bed frame components to the 3rd floor. The platform crashed down the shaft, killing both workers who had been guiding the cargo. The factory owner expressed appropriate regret and resumed operations the following day with a replacement rope rated for higher tensile strength. Such incidents occurred monthly throughout the Hudson River Industrial Corridor. Hemp rope, regardless of diameter or fiber quality, eventually deteriorated under repeated stress loading. The breaking point was a matter of physics, not opinion. Into this environment of calculated limitations stepped Elisha Graves Otis, a 41-year-old master mechanic whose entire professional life had been spent solving problems that other men accepted as permanent conditions. Born on a hardscrabble Vermont farm where broken equipment meant failed harvests, Otis had developed the engineer's fundamental mindset. Every mechanical system could be improved if you understood its failure points clearly enough. His formal education had ended at age 15, but 3 decades of repairing sawmill machinery, flour mill gear trains, and textile mill power transmission systems had taught him to see mechanical problems as puzzles waiting for systematic solutions. The Mays and Burns bedstead factory in Yonkers presented Otis with such a puzzle in the autumn of 1852. Josiah Mays, the company's owner, needed to move heavy iron bed frames and wooden headboards from the ground floor manufacturing area to the second floor finishing department. A standard industrial hoist would solve the immediate problem, but Mays had seen too many rope failures to accept the conventional death trap. Instead of purchasing an existing system, he approached his master mechanic with a direct challenge: design something that wouldn't kill his workers. Otis spent 3 weeks studying the mechanical principles behind rope failure before beginning his design work. Hemp fiber stretched under load, creating microscopic tears that accumulated over thousands of lifting cycles. No visual inspection could detect the internal damage until the moment of catastrophic failure. The solution, Otis realized, required abandoning the assumption that rope strength was the critical safety factor. Instead, he would design a system that could function safely even after total rope failure. The breakthrough concept emerged from his experience with railroad brake systems. Spring-loaded mechanisms could engage automatically when tension decreased beyond a predetermined threshold. Otis designed a tough steel wagon spring mechanism that connected to spring-loaded pawls positioned alongside ratcheted guide rails. Under normal operation, rope tension kept the pawls retracted, allowing the platform to move freely up and down the shaft. If the rope broke, the sudden loss of tension would release the spring-loaded pawls, which would immediately wedge into the ratcheted rails and stop the platform's descent within inches. The engineering specifications were precise and practical. 2 U-shaped wagon springs, each rated for 2,000 pounds of tension load, connected through a lever system to spring-loaded pawls machined from tool steel. The guide rails featured 1-inch ratchet teeth cut at 45-degree angles into seasoned oak timber. The entire safety mechanism added exactly 18 pounds to the platform's weight and cost $100 to manufacture. Double the price of a standard rope hoist, but a fraction of the cost of a single worker's death. By November 1852, Otis had installed his first safety hoist at the Mays and Burns factory. The device lifted 800-pound loads smoothly and quietly, with the safety mechanism completely invisible during normal operation. Factory workers, initially suspicious of any new machinery, quickly gained confidence as the system demonstrated its reliability through hundreds of lifting cycles without incident. Word of Otis's innovation spread through Yonkers' industrial community, but the initial market response proved disappointing. Local factory owners praised the mechanical ingenuity while questioning the economic necessity. Standard hoists had served manufacturing adequately for decades. The occasional rope failure, while regrettable, represented an acceptable cost of industrial operations. Spending twice the price for an unproven safety mechanism seemed like unnecessary expense for a problem that claimed only 2 or 3 lives annually throughout the entire Hudson River corridor. By September 1853, exactly 1 year after beginning his design work, Otis had completed and installed his first commercial safety elevator at the Crystal Palace Exhibition Planning Office in Manhattan. The installation demonstrated flawless mechanical performance, but generated 0 sales inquiries from the thousands of visitors who observed the system during the exhibition's planning phase. New York developers dismissed the safety brake as mechanical trickery with no practical application to commercial construction. European-trained engineers published critical assessments describing the spring mechanism as unreliable American novelty work that violated established principles of mechanical engineering. The crushing reality of market rejection settled over Otis's workshop by early 1854, despite live demonstrations that proved the safety mechanism's effectiveness. Orders remained virtually non-existent. He had sold exactly 8 elevators, all for freight applications, none designed for human passengers. The vertical city of his imagination remained locked behind 5-story limitations, not because the technology was impossible, but because human psychology refused to trust American innovation over European engineering orthodoxy. The financial crisis facing the Crystal Palace exhibition in early 1854 demanded theatrical solutions that conventional business wisdom could not provide. Phineas Taylor Barnum, newly appointed president of the Crystal Palace Association, inherited an enterprise bleeding money at a rate that would bankrupt the entire operation within 6 months. Daily attendance averaged fewer than 3,000 visitors, while the building's massive operating costs required at least 8,000 paying customers to break even. European industrial exhibitions drew crowds through displays of established manufacturing prowess, but American audiences demanded spectacle, drama, and the promise of witnessing something genuinely unprecedented. Barnum understood that technical demonstrations succeeded or failed based on their ability to capture public imagination rather than engineering precision. His decades of experience managing circuses, museums, and traveling shows had taught him that crowds responded to moments of visible danger followed by dramatic resolution. The key was creating genuine suspense about whether the performer would survive the demonstration, then delivering safety in a manner so conclusive that audiences would remember and retell the experience for years afterward. The meeting between Barnum and Otis occurred in March 1854 at the Crystal Palace planning offices, where the inventor's safety hoist operated daily without attracting significant attention from visitors. Barnum observed the mechanism during routine cargo operations and immediately recognized its theatrical potential. The concept of a man deliberately severing his own life support system, then trusting an untested mechanical device to prevent his death, contained all the elements of compelling public spectacle. More importantly, the demonstration would showcase American mechanical innovation in direct competition with European engineering traditions, creating a patriotic narrative that could draw crowds regardless of their technical understanding. The practical arrangements required substantial modifications to Otis's existing equipment. The exhibition demonstration demanded a platform large enough for Otis to stand comfortably while remaining visible to spectators positioned throughout the Crystal Palace's main hall. The mechanism also needed to function reliably under theatrical conditions, where lighting, crowd noise, and performance pressure could affect the operator's precision. Barnum allocated prime exhibition space near the building's central dome, where natural lighting would illuminate the demonstration clearly and acoustic conditions would carry Otis's voice throughout the hall. Otis spent 6 weeks constructing a specialized demonstration elevator specifically designed for the Crystal Palace exhibition. The shaft measured 18 feet in height, sufficient to create visual drama while remaining within the building's structural limitations. The platform dimensions provided 5 feet by 4 feet of standing room, large enough for Otis to move confidently while maintaining clear sight lines for spectators positioned at various angles around the demonstration area. The guide rails were machined from seasoned white oak and featured precisely cut ratchet teeth spaced at 1-inch intervals to ensure consistent engagement with the spring-loaded pawls. The safety mechanism itself required no modifications from Otis's standard industrial design, but the demonstration setup needed additional engineering considerations. The suspension rope was positioned to snap cleanly when severed by an axe blow, eliminating any possibility of partial failure that might compromise the dramatic effect. The spring-loaded pawls were adjusted to engage within exactly 4 inches of rope failure, providing sufficient drop distance to demonstrate genuine free fall while minimizing the mechanical shock when the safety brake activated. The weeks preceding the demonstration generated considerable advance publicity through newspaper advertisements and word-of-mouth promotion among New York's business community. Barnum's promotional materials emphasized the life-or-death stakes of the performance, describing Otis as a daring American inventor who would risk his life to prove the superiority of Yankee mechanical ingenuity over European engineering traditions. The marketing campaign specifically targeted building developers, factory owners, and construction industry professionals, whose skepticism about elevator safety represented the primary obstacle to commercial adoption. Public interest exceeded Barnum's expectations as the demonstration date approached. Advance ticket sales indicated attendance would approach the Crystal Palace's maximum capacity of 12,000 visitors. Newspaper reporters from the Tribune, Herald, and Times requested exclusive interviews with Otis before the performance. Several European engineering consultants working on Manhattan construction projects announced their intention to attend, creating an international dimension to what had begun as a simple product demonstration. The morning of May 23, 1854, arrived with unseasonably warm weather that filled the Crystal Palace's iron and glass structure with bright sunlight and oppressive humidity. Spectators began gathering around the demonstration area 3 hours before the scheduled performance, with the most prominent positions occupied by well-dressed building developers and formally attired. European engineers who viewed the proceedings with obvious skepticism. Working-class factory owners and construction foremen filled the remaining space, their practical experience with industrial hoists providing them with intimate knowledge of exactly how catastrophic rope failures typically concluded. Otis appeared at the demonstration site wearing his standard work clothes rather than theatrical costume, a deliberate choice that emphasized his identity as a practicing mechanic rather than a professional entertainer. His assistants had positioned the necessary tools and equipment with theatrical precision, including the sharp-bladed axe that would sever the suspension rope and trigger the safety mechanism. The crowd's conversation gradually diminished as Otis began his ascent to the platform, the silence reflecting genuine uncertainty about whether they were about to witness a successful demonstration or a public death. The platform rose smoothly to its full 18-foot height, carrying Otis well above the heads of the assembled spectators. From that elevation, his voice carried clearly throughout the hall as he began explaining the mechanical principles behind his safety brake system. The technical details were deliberately simplified for the mixed audience, but he emphasized the fundamental engineering challenge, creating a mechanism that could prevent catastrophic failure even when the primary load-bearing component failed completely. The demonstration reached its climactic moment when Otis raised his hand and called for silence throughout the hall. 12,000 spectators held their collective breath as his assistant positioned the axe blade against the hemp rope that represented the sole barrier between the inventor and a potentially fatal fall. The next few seconds would either validate years of engineering work and design refinement or destroy forever the credibility of American mechanical innovation in the elevator industry. Otis gave the signal. The axe blade swept downward. The rope parted with a sharp crack that echoed throughout the Crystal Palace's iron framework. The platform dropped exactly 4 inches before the spring-loaded pawls engaged the ratcheted guide rails with a solid metallic thunk that resonated through the sudden silence. Otis remained standing, unharmed and triumphant, as he delivered the line that would be quoted in newspapers across the country. "All safe, gentlemen, all safe." The immediate aftermath of the Crystal Palace demonstration generated newspaper coverage that reached every major city from Boston to Charleston, but commercial orders arrived with frustrating deliberation. Throughout the remainder of 1854, Otis received inquiries from factory owners and warehouse operators who had witnessed the rope-cutting spectacle, yet most conversations concluded with polite expressions of interest rather than binding contracts. By December, total sales reached 8 elevators, generating revenue of $1,200 against manufacturing and demonstration costs exceeding $2,000. The gap between public acclaim and commercial adoption revealed the persistent divide between theatrical success and business confidence. The fundamental obstacle remained psychological rather than technical. Building developers and factory owners praised Otis's mechanical ingenuity while questioning whether the safety mechanism would function reliably under daily operational conditions. The Crystal Palace demonstration had proven the concept under controlled circumstances, but industrial applications involved thousands of lifting cycles, varying load weights, and operational stresses that could not be replicated in a single theatrical performance. European engineering consultants continued publishing technical critiques that questioned whether American spring steel could maintain consistent tension over extended periods of use. Throughout 1855, Otis methodically addressed these concerns through incremental design improvements and expanded field testing. He installed demonstration elevators at 3 additional manufacturing facilities, accumulating operational data that documented mechanical performance across varying conditions. The results supported his engineering confidence. After 6 months of daily use, the safety mechanisms showed no signs of spring fatigue or pawl wear that would compromise their effectiveness. The ratcheted guide rails maintained precise engagement angles despite repeated activation cycles during routine maintenance testing. The commercial breakthrough began with an unexpected inquiry from Eater Haughwout, owner of Manhattan's most prestigious china and glassware emporium on Broadway. Haughwout had observed the Crystal Palace demonstration with the calculating eye of a luxury retailer who understood that his wealthiest customers expected both elegance and convenience. His 5-story building at the corner of Broadway and Broome Street served clientele that included Mary Todd Lincoln, prominent banking families, and European diplomatic representatives who demanded the finest imported merchandise displayed in appropriately refined surroundings. The challenge Haughwout presented transcended the industrial applications that had defined Otis's previous work. A passenger elevator serving luxury retail customers required engineering specifications that prioritized smooth operation, quiet performance, and absolute safety over the heavy lifting capacity needed for freight applications. The mechanism would carry well-dressed ladies in elaborate gowns, elderly gentlemen with walking sticks, and foreign visitors whose comfort and safety would directly impact the store's reputation among New York's social elite. Otis spent the winter months of 1856 developing passenger elevator specifications that addressed these refined requirements. The platform dimensions expanded to accommodate multiple passengers wearing the voluminous clothing styles of the period. The guide rail system was redesigned to eliminate the mechanical noise that characterized industrial hoists, incorporating felt padding and precision machining that reduced operational sound to levels appropriate for a luxury retail environment. The safety mechanism retained its core spring and pawl design while adding refinements that ensured smooth engagement without the jarring impact that freight elevators could tolerate. The most significant innovation involved the power system. Industrial elevators relied on manual operation or steam engines that generated considerable noise and vibration. Haughwout's passenger application required a steam-powered hydraulic system that could provide smooth acceleration and deceleration while maintaining the quiet operation necessary for an elegant shopping experience. The hydraulic mechanism used steam pressure to drive a piston that lifted the elevator car through a system of pulleys and counterweights, with the safety brake serving as backup protection against cable failure. Construction began in January 1857, with installation scheduled for completion before the spring shopping season. The engineering specifications reflected the luxury application. The elevator car featured upholstered seating for 6 passengers, polished brass fittings, and mahogany wood paneling that matched the store's interior decor. The operational parameters included a maximum ascent speed of 40 feet per minute, approximately 15 seconds travel time between floors, and a total capacity of 1,000 pounds, including passengers and operator. The installation process attracted considerable attention from Manhattan's business community, as the Haughwout Building would house the world's first commercial passenger safety elevator. Skeptical observers gathered daily to watch construction progress, with particular attention focused on the safety mechanism installation. European engineering consultants published advanced critiques predicting that passengers would refuse to trust their lives to an untested American contraption, regardless of theatrical demonstrations or mechanical specifications. March 23, 1857 marked the elevator's first operational day, with Haughwout personally conducting initial test rides before opening the system to customers. The New York Tribune reported the event with barely concealed amusement. Among the novelties we noticed is an elevator to be worked by steam, which is to be furnished with a sofa and carriage to carry ladies from one floor to the other. The tone reflected widespread skepticism about whether New Yorkers would actually utilize mechanical vertical transportation for routine shopping activities. Customer response proved more cautious than Haughwout had anticipated. Many visitors examined the elevator car with curiosity, but chose to climb the traditional stairs rather than trust the mechanical system. The elevator operator, trained by Otis personally, spent considerable time each day explaining the safety mechanism to hesitant customers who questioned whether the spring-loaded pawls would actually engage if the cable broke. Several prominent customers explicitly refused to ride the elevator, preferring the familiar exertion of stair climbing to the perceived risk of mechanical failure. The operational challenges extended beyond customer psychology to encompass practical concerns about elevator etiquette and social protocols. Mixed-gender passenger loading raised questions of propriety that had no precedent in American social customs. The confined space of the elevator car created uncomfortable proximity between strangers who would normally maintain appropriate social distances. The necessity of trusting one's safety to a mechanical operator rather than personal physical effort challenged fundamental assumptions about individual autonomy and social control. Despite these obstacles, daily elevator usage gradually increased as customers gained confidence through repeated successful operations. The mechanism's smooth performance and obvious safety features slowly overcame initial reluctance, particularly among elderly customers who appreciated avoiding the physical exertion of climbing multiple flights of stairs while carrying purchases. The elevator's novelty also attracted curious visitors who rode the system specifically to experience this unprecedented form of mechanical transportation. By summer 1857, the Haughwout elevator had achieved routine operational status, carrying dozens of passengers daily without incident. The success generated inquiries from other luxury retailers and commercial building developers who recognized the competitive advantage that passenger elevators could provide in attracting customers and tenants. More importantly, the installation had proven that American elevator technology could function reliably in applications that demanded absolute safety and refined performance standards that exceeded industrial requirements. The winter of 1860 to 1861 brought an unusually harsh diphtheria epidemic to the Hudson River Valley, claiming victims across all social classes with democratic ruthlessness. Elisha Otis, whose chronic health problems had plagued him throughout his adult life, contracted the disease in late March and died on April 8, 1861, at age 49. His death occurred just 4 months after receiving patent number 27,447 for his safety brake mechanism, the legal recognition he had pursued for nearly a decade. The timing seemed cruelly ironic. Recognition arrived precisely when the inventor could no longer benefit from the commercial success that had eluded him for so long. The Otis Elevator Company passed immediately to his two sons, Charles and Norton, who inherited an enterprise with 25 operational elevators scattered throughout Manhattan and Brooklyn, outstanding debts exceeding $3,000, and a manufacturing operation that employed fewer than a dozen workers. The brothers possessed business acumen that their father had lacked, but they faced immediate challenges that threatened to destroy the company before they could establish stable operations. The outbreak of civil war in April 1861 disrupted construction activity throughout New York, as building developers postponed major projects indefinitely, and existing elevator customers questioned whether mechanical systems represented wise investments during uncertain economic times. Charles Otis, the elder son at 26, had worked closely with his father during the final years, and understood both the technical principles behind elevator design and the commercial obstacles that had limited market acceptance. Norton, 3 years younger, brought systematic organizational skills that complemented his brother's mechanical knowledge. Together, they recognized that sustaining their father's innovation required transforming a craftsman's workshop into a manufacturing business capable of producing standardized elevators at prices that could compete with European imports while maintaining the safety standards that distinguished American designs. The economic disruption caused by the Civil War extended far beyond immediate construction delays. Banking institutions, uncertain about the conflict's duration and financial impact, restricted lending for commercial projects that could not guarantee rapid returns on investment. Building developers who had shown interest in elevator installations during the late 1850s postponed decisions indefinitely, preferring to maintain existing 5-story limitations rather than risk capital on untested vertical construction methods during wartime uncertainty. The psychological impact of national crisis also affected public confidence in mechanical innovations. Elevator safety, which had always faced skepticism from potential passengers, seemed like an unnecessary risk during a period when daily newspapers reported battlefield casualties and civilian hardships. The mechanical complexity that Otis had presented as a solution to rope failure now appeared as an additional vulnerability in a world where simple, proven technologies offered greater reliability than sophisticated American innovations. By 1863, the Otis brothers had sold fewer than 40 elevators since inheriting the company, barely maintaining sufficient revenue to cover basic manufacturing costs and employee wages. Several competitors had entered the elevator market, offering cheaper systems that eliminated safety mechanisms in favor of lower prices and simpler installation requirements. European engineering firms established American offices and promoted traditional rope and pulley systems that claimed superior reliability through time-tested design principles rather than unproven mechanical innovations. The most serious challenge emerged from changing construction economics during the war years. Manhattan real estate prices, which had driven demand for vertical building solutions during the 1850s, stagnated as business activity shifted toward military contracts and war-related manufacturing. The economic incentive for constructing tall buildings disappeared when ground floor space could accommodate most commercial requirements at stable rental rates. Building developers who had previously considered elevator installations as competitive advantages now viewed them as unnecessary expenses that reduced profitability without providing corresponding benefits. The Panic of 1873 delivered the decisive blow to elevator market expansion that had been building throughout the post-war Reconstruction period. The financial collapse, triggered by railroad overspeculation and European investment withdrawals, created a depression that lasted until 1879 and virtually eliminated new construction activity throughout American cities. Manhattan building permits, which had averaged over 800 annually during the pre-war boom, fell to fewer than 200 per year during the worst Depression years. The psychological impact of economic collapse extended the market contraction beyond rational financial calculations. Building developers who had survived the panic became extraordinarily risk-averse, avoiding any innovations that could not demonstrate immediate and substantial returns on investment. Elevator installations, which required significant upfront capital and ongoing maintenance costs, represented exactly the type of speculative expense that Depression-era business owners eliminated first. The safety benefits that had gradually won acceptance during the 1860s seemed irrelevant when building heights remained limited to traditional five-story maximums that required no mechanical assistance for vertical transportation. Several prominent Manhattan buildings actually removed their elevators during the mid-1870s to reduce operational expenses and eliminate maintenance costs that could not be justified by rental income from upper floors. The Tribune Building, Western Union Building, and Equitable Building stood as isolated exceptions to the five-story limitation. But even these structures faced financial pressures that questioned the economic viability of vertical construction in American cities. European engineering publications seized upon the American elevator industry's struggles as validation of their long-standing skepticism about mechanical solutions to architectural challenges. Technical journals published detailed analyses proving that tall buildings could never achieve economic viability in American business conditions, citing operational costs, safety concerns, and tenant psychology as insurmountable obstacles to vertical urban development. The mechanical ingenuity that Americans had celebrated during the Crystal Palace demonstration now appeared as misguided innovation that violated fundamental principles of sound construction practice. By 1875, only scattered tall buildings existed in Manhattan, and critics confidently declared the elevator a passing fancy, unsuited to American commercial requirements. The vertical city that Elisha Otis had envisioned seemed like an impossible dream, defeated not by technical limitations but by economic reality and human psychology. His sons maintained the company through custom installations and industrial applications, but the transformative potential of passenger elevators appeared permanently constrained by forces beyond mechanical engineering solutions. The economic recovery that began in 1880 transformed Manhattan's construction landscape with mathematical precision that validated every prediction Elisha Otis had made 3 decades earlier. Land values on Lower Broadway soared from $80 per square foot in 1878 to over $300 by 1882, creating financial pressures that made vertical expansion not merely advantageous, but economically essential for profitable development. Building developers who had dismissed elevators as unnecessary expenses during the Depression years suddenly faced calculations where constructing upward represented the only viable method for generating adequate returns on increasingly expensive Manhattan real estate. The Otis brothers had survived the economic downturn through methodical business management and incremental technical improvements that positioned their company to capitalize on the construction boom. Charles had refined the safety mechanism's manufacturing process, reducing production costs while improving mechanical reliability through precision machining and standardized component specifications. Norton had established distribution networks and customer service protocols that could support rapid expansion when market demand returned. By 1880, the company employed over 60 workers and maintained inventory sufficient to fulfill large orders without extended delivery delays. The breakthrough application came from an unexpected source: the Equitable Life Assurance Building at 120 Broadway, which had operated successfully as an 8-story structure since 1870 but now required expansion to accommodate the insurance company's growing workforce. Rather than purchasing additional expensive Manhattan real estate, Equitable's directors chose to add 4 floors to their existing building, creating the first 12-story office structure in American commercial history. The expansion required multiple passenger elevators capable of transporting hundreds of office workers daily between floors that extended far beyond the Siam limits of stair-climbing convenience. The engineering specifications for the Equitable installation represented the most ambitious elevator project yet attempted in American construction. 6 passenger elevators, each with a capacity of 1,500 pounds, would serve 12 floors with travel speeds of 120 feet per minute, 3 times faster than the Haughwout store's pioneering system. The safety mechanisms incorporated all of Charles Otis's design refinements, including dual spring systems, reinforced guide rails with precision-cut ratchet teeth, and emergency stop controls that could be activated by passengers in case of mechanical problems. The installation process required 6 months of construction work that attracted daily observation from Manhattan's architectural and engineering communities. European consultants who had confidently predicted the failure of American vertical construction during the Depression years now watched with grudging interest as Otis elevators demonstrated capabilities that exceeded their theoretical calculations about passenger psychology and mechanical reliability. The smooth, quiet operation of the hydraulic drive systems eliminated most of the noise and vibration that had characterized earlier elevator designs, while the safety mechanisms provided visible reassurance that addressed lingering public concerns about rope failure. The commercial success of the completed Equitable building exceeded all projections and fundamentally altered Manhattan real estate economics. Upper floors, which had traditionally rented for half the price of ground-level space, now commanded premium rates of $4 per square foot compared to $2.50 for street-level offices. The reasons were immediately apparent to tenants: better views of New York Harbor and the Hudson River, cleaner air above the dust and noise of street traffic, and greater privacy from the commercial bustle that characterized ground-floor spaces. The psychological transformation of Manhattan's business community occurred with startling rapidity once the Equitable building proved the economic viability of vertical construction. Building developers who had avoided elevator installations for 2 decades suddenly competed to secure Otis contracts for new construction projects. The company's order backlog extended beyond their production capacity by early 1881, requiring expansion of manufacturing facilities and workforce to meet demand that had materialized seemingly overnight. The architectural implications extended far beyond individual building projects to encompass fundamental changes in Manhattan's urban landscape. Trinity Church, which had dominated the city's skyline at 280 feet since 1746, suddenly appeared dwarfed by the Tribune Building's 260 feet and the Western Union Building's 230 feet. The psychological impact was profound. For the first time in New York's history, commercial architecture challenged religious structures for visual prominence in the urban environment. The engineering achievements that made these heights possible reflected continuous refinements to Otis's original safety brake concept. The spring-loaded pawl mechanism remained fundamentally unchanged, but manufacturing precision had improved dramatically through the use of machine tools that could cut ratchet teeth to tolerances measured in thousandths of an inch. The guide rail systems now utilize steel rather than wood, providing greater durability and more consistent engagement with the safety mechanisms. Steam-powered hydraulic systems had been refined to deliver smooth acceleration and deceleration that eliminated the jarring movements that had characterized early elevator installations. The market response to successful tall building operations generated a construction boom that transformed Manhattan's economy and established elevator installation as an essential component of commercial development. By 1883, over 2,000 Otis elevators operated in New York buildings alone, serving structures that ranged from modest 6-story commercial buildings to 12-story office towers that housed hundreds of workers on upper floors that had been economically worthless 2 decades earlier. The social implications of vertical construction extended beyond economics to encompass fundamental changes in urban work patterns and residential preferences. Office workers who had previously accepted five-story limitations as natural constraints now took for granted the ability to work on floors that provided commanding views of Manhattan's expanding commercial district. The elevator operator became a recognized profession with specific training requirements and salary scales that reflected the responsibility of safely transporting dozens of passengers daily. The vindication of American engineering innovation proved particularly satisfying to the Otis brothers, who had endured years of European criticism and domestic skepticism about their father's mechanical solutions. European architectural publications that had dismissed safety brakes as unreliable American novelty work now published detailed technical analyses of Otis elevator systems, seeking to understand the engineering principles that had enabled vertical construction on a scale that European cities had not attempted. The transformation from hemp rope limitations to steel-guided safety reached its symbolic conclusion in 1885 when the completed Tribune Building rose to 260 feet, definitively establishing that Manhattan's future lay not in horizontal expansion across expensive real estate, but in vertical development that maximized the economic potential of every square foot of urban land. What European experts had declared impossible, American determination and mechanical ingenuity had made inevitable, creating the foundation for the skyscraper age that would define urban architecture for the next century.